Before we start today's lesson, let's look at this table that depicts the number of boys and girls doing arts or science. We must realize that this is a table of frequencies, and that we can look at it as simply a statistics data, or we can use it to calculate probabilities. For example, we can ask the question, if a student is picked at random, what's the probability of choosing a boy? And in that case, we know that the sum of the boys is 60, the sum of the girls is 90, and the total is therefore 150. So the probability of choosing a boy is 60 over 150. And if you simplify it to the lowest terms, you get 2 over 5. And this provides us with a link between statistics and probability. We used statistics to calculate a probability. And the point that I would like to stress is that we can consider probability as relative frequency. What do we mean by relative frequency? It's simply the favorable outcomes, the favorable frequencies divided by all the possible outcomes, the total frequency. So it's a ratio between the frequency of whatever you're looking for and the frequency of the entire population. With this in mind, let's move on. We're going to look at the difference between theory and practice, the difference between probability and statistics in a way. And we want to consider a fair four-sided die, something like that. And what you read is one value, which is probably the value at the bottom, the hidden value, or one of these. So basically, you can either score a 1, a 2, a 3, or a 4. And since it's a fair die, then the probability is 0.25 of each of those scores. And since the probabilities are equal, we call them uniform. Now, when you roll this die 100 times, or when you roll 100 of those dice, you don't expect to get exactly 25 ones, 25 twos, 25 threes, or 25 fours. You get variation in real life. Let's do this experiment. I here can choose the number of sides on the dice. So I chose 4, and I'm going to throw 100 of them. Or in essence, I can roll the same die 100 times. And if I start and I stop, I end up with a sum of 254. And that means that the sum of the scores is 254. If I do it again, I get 236, significantly less. If I do it again, I get 257, a bit more. So every time I define my experiment as throwing the die 100 times, I get a different sum. So it's highly unlikely to get 25 ones, 25 twos, 25 threes, 25 fours in practice. Of course, as you perform, as the number of times you throw the die increases, you will get something closer to equal outcomes. Let's say that we have this experimental outcome. This is the value of the variable, if I define my variable as the score, and this is the frequency. So as you can see, I'm rolling the die 100 times, and I'm getting 26 ones, 23 twos, 24 threes, and 27 fours, which is reasonable. Let me try to calculate the mean. The mean score, that is the score per throw. is equal to, as you know, this is a frequency table, so 26 times 1 plus 23 times 2 plus 24 times 3 plus 27 times 4, all divided by 100. And for reasons, of course you can calculate this immediately, but for reasons that will become shortly clear, this can be thought of as one times 26 over 100 plus 2 times 23 over 100 plus 3 times 24 over 100 plus 4 times 27 over 100. And therefore, the mean score in this case, if you calculate this, you'll get 2.52. In the case of this row, our mean was therefore 2.57 because we're dividing the sum by 100. In this case, it's 2.65. In this case, it's 2.76, 2.47, and so on. Now, this is what we would call an experimental outcome. Now, before you perform the experiment, one might ask, what mean would you expect to get? For that purpose, because you have not done the experiment yet, you would just go to probability. Let's consider the theoretical outcome. We have here our outcome, which is x. It can be 1 or 2 or 3 or 4. And the probability that your score is equal to x is 0.25 for each of them, because it's a uniform distribution. And if I calculate the theoretical mean, that would be 1 times 0.25 plus 2 times 0.25 plus 3 times 0.25 plus 4 times 0.25, giving me 2.5 exactly. Now, what is the relation between this theoretical outcome and this experimental outcome? If you consider this, the 26 over 100, it is the experimental probability of getting a 1 based on this frequency table. So it's the relative frequency. Which is basically probability. So what we have is that this table tells me a kind of experimental probability, and I can, using statistics, calculate the actual mean that I got. But since the probability here is the theoretical value, I'm getting a theoretical mean, which is what I would expect to get before I start throwing the die. That's why we call it the expectation of x. E of x. Sometimes they refer to it as mu, the theoretical mean. And this presentation, I hope, makes it clear that there is a very strong relationship between probability and statistics, between the theory of the situation and the actual situation. So, in summary, our lesson basically states that the expectation of x, which is the theoretical mean of x, which is the mean that you would expect to get if you play this game indefinitely for a very large, very large number of times, is basically the sum of the value of the variable times its probability, which is exactly what we did here. The value of the variable times its probability. That's your theoretical outcome. Remember, we also have the fact that the sum from I equals 1 to n of pi, the sum of the probabilities in the probability distribution table is 1. So two rules up to this moment. The sum of the probabilities equals 1, and the theoretical mean is equal to the sum of the product of the variable times its probability. Let's look at an example. We have a probability distribution. The variable can take the values 1, 3, and 5, and the probability that capital X, the discrete random variable, can take the value of X is 2 over 5 A 1 over 10. Obviously, what's the value of A? We know that the sum is 1, so 1 equals, let's convert them to decimals, it's easier, 0.4 plus A plus 0.1, that tells us A equals 0.5. B, the mode of the distribution, it's obviously 3 because this is the highest probability. And if I add what's the median, .4, we haven't reached 0.5 yet, plus 0.5, we overshot 0.5, so the median is also 3. Now what is the mean of the distribution? Meaning, if you perform this experiment that results in this outcome an indefinite number of times, what is the mean score that you'll get, that you'll expect to get over a very large number of trials? It's simply 1 times 2 over 5 plus 3 times 0.5 plus 5 times 1 over 10 is 0.1. So this is 0.4 plus 1.5 plus 0.5, giving us a total of 2.4. So every time you play, you'll get a score, but if you play an indefinite number of times, your mean score would be 2.4. And that's the idea.